let us today, right, look at these special cases. Okay, two special cases which will throw some light on what's happening. Special cases. One is what is called the parallel camera case. The parallel cameras. So, right, what we want to know is if you have parallel cameras, so that effectively means that you have two cameras, your left and right, and then your optical center is here, and these two are actually separated, of course, by some Tx or something, and that's all. Okay, so in the sense that that this separation is exactly along right on this one image plane. Right, you have the x-axis of the image plane, just is it translating along that. Okay, you're not rotating, you're not moving forward, you're not doing anything. Right? You're just doing a baseline. That's called a baseline, right? So this is the best sort of stereo situation which you can have. This is the one that most people will use or will want to use, where you have two parallel cameras, where we have kind of these parallel cameras. So this is the this is the type which is actually non-converging. The other way to call them is non-converging cameras. And the idea is that, right, we want to know in such a case, where should we be searching, right? Really, the whole idea is that you have a point. So we saw what actually fundamental matrix. Oh yeah, right. Prior to that, just one sort of a quick this one on that the view synthesis thing, because somebody later got confused with what I said. They said the fundamental matrix you said will relate a line to a point, but now you are relating a point to a point. So the view synthesis, right, all that I was saying was that if you have a view of a scene, right, from a certain viewpoint with a depth map, right, that is key. That means you have some stereo setup with which you have been able to estimate a depth map, okay, with respect to one of the views. Let's say with respect to the left camera, you have a view, you have a depth map. And that means depth map means you know that how far away, right, right, is each point. Okay, so along this z axis, you know how far away is each point. That is your depth. That is all assuming that your optical axis aligns with your z and so on, right, which is what we've been assuming all through. Now, when you have that, now the point is, if I virtually place a camera somewhere else and I want to see what the scene looks like, of course I cannot go too far away. Okay, because there should be a lot of overlap between the two, right? Otherwise, you will see things that you cannot see in the first frame, right? So it's actually a virtual camera, right? So it's not even capturing anything; it's a virtual camera. So when you actually keep it there, right, you are now trying to ask what will the scene look like if I saw it from there, right? And you can actually do it through the image coordinates, right, in the following. I mean, one thing is you can go through 3D, but you can also show very simply that if for this left camera, right, if you had x tilde is equal to what is it, some k left, and then I 0, and then x tilde, right, where this x tilde is actually x, y, z, but now the z is known. Okay, that's a big difference now. The z is known now. That means the depth map is given to me. I have somehow calculated that I have another camera which is a stereo pair. I have calculated. We still haven't talked about how to compute depth, but let's say we can, right? Given a disparity, let's say we can compute depth. Now that z is known. Okay, that is a key difference. Okay, between synthesizing a view versus whatever else, right, we are actually doing. I mentioned about this view synthesis because I felt that that is something that you people must be wondering. People talk about novel views. They say that the scene looks like this when seen from there and all. I was just thinking that after all, right, with stereo, with so much that you have learned, you should be able to. That's just one step away. So having come this far, I thought it should be easy to just let you know that I'm not going to ask you anything on this in the exam, but just to let you know that such a thing is just one step away. So now for example, right, now if you actually the way you do view synthesis is that you have an image, right, with respect to the left camera, and let's say, okay, this need not be right there. Let's say this is kept somewhere else, and this is actually a virtual camera. Right, so we are kind of keeping it there at some R&D, right, from with respect to the first camera center, optical center. Now, when you are saying that, right, so that means you specify R, you specify T, right, and you are saying that how will the scene look like. So it basically means that I need to know that, right, given this 3D scene that I am seeing, right, I need to know that, right, if this guy back projects, right, through my whatever, right, I mean, here is my camera center, let's say, right, when I get a back project array from a coordinate in the image, right, it will go back project means it will go all the way, but now I know the Z, so I know where to stop, right, because the Z is given to me for every point, right, that's the depth map. That means for every point, right, I know how far away is that particular 3D point from this camera. So which means that when I back project, I know where to stop on that ray because I know the Z. And now right, all that I need to do is from that point onwards, right, whatever is this camera center, right, I need to simply come there. Okay, let's say, right, that's my C dash, and then wherever it hits this ray, this projected ray hits the image plane there, that's where this point is. And then the intensity should be exactly whatever is the intensity here, let's say, whatever, right, some point here in the image plane, that intensity should then be copied there, and then that is the intensity of this point, right, in 3D. Its image is with us, and all that we are doing is transferring that intensity to another grid where it's a kind of a virtual view, right. And you can think of a corresponding point as, okay, now what typically is done is, since you are projecting from an image coordinate here, so you scale this by Z. So you get like 1 by Z x tilde is equal to 1 by Z KL, and then this can be simply rewrite, you can rewrite this as XYZ. X tilde is 4 dimensional. So it becomes XYZ, and this is your actual image coordinate now. I mean, that is the coordinate that I am going to pick from here, and you are going to say back project. And therefore, you can call that as, let's say, X, put sort of, right, a double dash below, just to indicate that it's actually the actual image coordinate. It's like XY1. And then this becomes like 1 by Z KL XYZ, sorry, capital XYZ. And then when you want to go to the other point, right, that will be like, whatever, X tilde dash, which is a corresponding point for that 3D. Right. So, X tilde dash is now what, some K virtual, you can assume some intrinsic camera matrix if you wish. Then you have an R and T which you specify, and then, right, this goes through the same as X tilde, right, because that's that ray that's coming back. And now this is called the camera pose together. It's called the camera pose. R and T, right, will tell you the camera pose. That's what people will tell when they say that the camera is at a different place. They'll say that it has a different pose. They won't say it has a rotation and translation and all. The word used is pose, right. So there is a pose for that camera, and all that you have is KV, and then you have a pose, and then this X tilde vector is but XYZ1, right, the same XYZ, but that same XYZ is nothing but from here, right, I can write it as KL inverse Z X tilde, which is the image coordinate. And always you see, remember that I know the Z here. This is not a case of unknown Z. Okay, therefore I can do all this. So then this becomes Z KL inverse X tilde, and then 1, and then this is your X tilde dash. Okay, so you have pose, you have the depth. This Z is the depth. You have the camera intrinsics, and then you have an image coordinate. So you can directly go from the left image coordinate to the kind of virtual image plane, and you can synthesize the view. Okay, but always remember that, right, even though somewhere the fundamental matrix, right, you may be able to see here and all, but then it's not that. Okay, fundamental matrix again maps lines to points. This one is actually a point to point mapping now, because Z is known, because Z is given, right. This is a point to point mapping, therefore this should not be confused with what I said the other day about the fundamental, because somebody had this doubt. They said, oh, you said fundamental matrix line and point, now you are saying point to point. This is not a fundamental matrix anymore, right. This Z and all is coming in now, the actual value of Z, and therefore this is how you actually synthesize a new view. I mean, right, if you read any paper, right, where they do view synthesis, this equation will be central there, and if you are wondering where it comes from, this is where it comes from, right, follows in a very simple way. Yeah. So all that I am saying is, right, see, the fundamental matrix is also something like, yeah, I mean, I know, right, it's actually a cross product and so on, but all that I am saying is, one should not think that the R and T, right, which are actually sitting here, right, they all kind of I think, okay, right, I think probably the student, right, did not put forward the confusion correctly. The confusion was that somewhere I said line to point correspondence and somewhere I said point to point. So, somewhere, right, that so the fundamental matrix confusion that there was line to point, suddenly I am talking about point to point. I am not saying this is fundamental matrix, they are saying that that should not be confused with this is a different thing altogether. Okay, that is all.
Sir, I had one more doubt. Second image plane, that's a x dash tilde.
What? Which one? Which inverse mapping?
No, if there is a point x tilde in the first image.
First image plane is, yeah, x tilde.
So now, okay. So if there is an x tilde itself, that will be unique point only in that.
Yeah, because you are stopping at some z, no?
Okay.
You know the z, right? You can only go so far, and you have to stop there. I mean, you can't go farther. You can't go. There are some complications that can happen, which I don't want to kind of go into. Okay, when you change the view, right? For example, right, it's like saying that on a point, right, I might be able to see in this image plane from this view, but when I change my view, right, there could be some other point sitting in front of it, exactly in front of it. So when I back project, I don't see that point. In fact, I see the point in the front. That's called occlusion. Such things cannot, let's not get into all that, right? Then we will go nowhere. Okay, so the parallel camera case, right, is like this. Okay, so we want to know as to what kind of a search will then happen and where will be the epipole and so on, right? So in this case, so the way to kind of, right, do it is as follows. So yeah, so let's go back and write down the fundamental matrix. So we had, so this is the right camera, this is the left camera. So what was the fundamental matrix equation? Something like this, right? Kr minus T, and what is it? This one, the T cross R, and I think KL inverse, right? This is what it was. Okay, now when it is a parallel camera case, right? That means R is identity. You did not say rotate. What about T? The vector. This is a vector T. T is simply Tx00. Right, because you have only a base, you have only translated along the plane of the camera along the x axis. So there is only a Tx shift, there is no 0, there is no Ty, there is no Tz, and therefore, right, what will be this say T cross when you kind of write it down as a matrix? What is 0 0 0? I think it's 0 0 minus 1 and 0 1 0, something like that, right? Something like that should be your Tx. Okay. Now if you right, I am going to take a simple case here. I am going to say that Kr is equal to Kl, right. I am going to take a typical stereo situation where you just translate the camera, but then whatever I am saying will still apply even if you take a full blown K not equal to Kr not equal to Kl. Right. This portion I am going to leave it to you to find, okay, because everything if we derive here, it will take a long time. I am just assuming that it is equal to K. I am in fact taking a very, very simple situation like F00, 0, F0, 0, 0, 1. Okay, but in reality this is not a condition, this is not a necessary condition for what follows. Okay, I am just taking it as a simple case because then we can do this Kr inverse and all very quickly and show something. Otherwise, if you take 5 parameter unknown in that K matrix, then that inverse and all, right, will be kind of clumsy. But whatever I am saying does not restrict it. So it does not mean that stereo means that same camera should be translated. You cannot change the camera and all. Okay, you can have two non-identical cameras. Perfectly okay. You can have all 5 unknowns thrown into K and K dash, no problem. Okay, but I am just taking it as a simple case here. So then what you can show is this F, right? I think this should be very straightforward to show. I just had the form here. So it's like 0 0 0 0 0 Tx by F and 0 minus Tx by F, and then what is it? 0. Yeah, correct, minus Tx and Tx. Yes, you are right, minus Tx and Tx. Oh, then I think even here, what is it, like minus Tx and the F, yeah, I think even here, I think it's minus Tx by F here and then a Tx by F. Anyway, it's equivalent up to any scale factor, but I think if you multiply this, what you will get, minus Tx by F there and then Tx by F in the bottom. Now, what you want to know is, okay, now we know that right, with this fundamental matrix which is relating P to P, what is it, PL to PR, right. So now if I take a point Okay, let's now right, I can actually scale this, okay, because like I said, right, the fundamental matrix is only known up to a scale factor. Therefore, I can equivalently write this as 0 0 0 0 0 minus 1 0 1 0, because it's known only up to a scale factor. So I can just knock off this T x by x and simply keep it in a simple form. If I take this and now right, what I want to do is I want to see as to where this takes a point, right. So I want to take an say x tilde, which is in my where is it, left or right? Left, right. From a left camera I take a point, and now I have what is it, 0 0 0 0 0 minus 1, right, 0 0 minus 1 0 1 0, and then I apply it on this x y 1. This will give me an epipolar line. It will give me L1 L2 L3 for the epipolar line corresponding to that point, right. And therefore, what will you have? You will have 0 minus 1 y. Okay, this is my L dash, right, corresponding epipolar line for that point. And now if I now take some, say take some, what should I take now? I should take some x tilde dash, right, and find out what condition should it satisfy for it to be on this epipolar line. And x tilde dash is coming from where? From the right image plane, right, and I want to know what condition should it satisfy for it to lie on this epipolar line. And what is that condition? That should be that it should lie on this line, right, which is like x tilde dash, dot product, right, with this guy should be 0. Okay, whatever, dot product or transpose or whatever. So then let's call that as x dash y dash 1, and then you have like 0 minus 1 y is equal to 0 for some point whose coordinates are x y in the first plane. And this means that, what does this mean? Minus y dash plus y is equal to 0, or it means y is equal to y dash. So what does it mean? Or y dash is equal to y, in fact, right, this is the other way, y dash is equal to y. So it actually means that only points that satisfy this condition, that their y dash is equal to y, right, can lie on the epipolar line. So what this means is that your search space is now exactly this. So if you pick any x comma y, sorry, not a line, if you pick a point here at some x comma y, now the corresponding point, right, lies exactly at the same y on this epipolar line, which is a horizontal line now, right. This is a special case because you have a parallel camera situation. Therefore, right, if you just pick a point which is at x comma y, you don't have to go up or down, or you don't have to go some angle and all, right. You just have to go look at the same row in the other image and sort of look for a match. And match you can do using cross correlation, whatever it is that you want to use, some patch, intensity, something you can do, right, which is simple. But the point is, right, so this right epipolar line, right, will go like that, and therefore, right, I mean, all these epipolar lines, right, I mean, will actually turn out to be horizontal. And the point is, right, so if you want to find out what is epipole, where is the epipole, right, I mean, for this arrangement, because epipole is a place where if you drop C to the other camera plane, wherever it intersects the image plane, that's your E dash, and if you do the other way around, that gives you your E, right. Now you know that, right, epipole E is such that, right, Fe should be equal to 0, and it is straightforward to show that if you just use an SVD or something, then this null of F, right, turns out to be 1 0 0. You can show that F times this is also 0, and SVD, if you do, right, this is what you will get as kind of your null. So which basically means that the epipole is that infinity. Okay, that means you can see that, no, it's a parallel camera case, right, it's a parallel camera case, and therefore, right, the right epipole will go both this one and that one, right, they'll both, so the epipole will be at infinity. Okay, and that's one way to know, actually, that's one way to know. If somebody, right, gives you a camera arrangement, and if you are able to compute the fundamental matrix, and if you find the null, right, that actually tells you what is the camera arrangement there, whether it's a converging camera situation or it is not, right. The epipole actually is very kind of powerful that way. And the other thing, yeah, right, so yeah, epipole at infinity, so yeah, so I think, right, this is a special case, this is a parallel camera case. Let's also look at, right, one more thing that is of interest typically. There is one other situation at which you can look at, which is forward translating camera. Forward translating camera. What is it like? Forward translating means you take a camera and walk along the optical axis, like this, right? You don't rotate, You don't go this way, just walk along the optical axis. So it's like this. I mean, right? I'm not kind of good at drawing and all. So imagine something like this. So your C can be here and your C dash can be there. Right. So this is your first camera. I won't call left right now. I'll call first and second, because there is nothing like left right now, or front and back if you wish. Right, front and back. Again, right, you can ask what kind of where do you think will be this epipole for this? This is a converging camera case. Converging cameras. Anyway, we will see, right? I don't think it's obvious, right? Fine. So let's see, right? Let's go the same way. So what do? You first compute the fundamental matrix Kr minus T T cross R KL inverse. Okay, and again use the same simplification. Again, it doesn't matter. Okay, you can take a general case, but I'll just take the simplified case where now T x, right, will take the form. So now, okay, now T itself, right? T itself is now what? 0 0 T z, because you are moving only along z, right? So 0 0 T z now. So it turns out that you will get 0. Yeah, so what do you get? You will get like 0 minus T z, 0, T z, 0 0 0 0 0. We can actually verify that this is correct. And now R is identity, of course, because you have not done any kind of a rotation. R is identity. Then this F takes up a form which will be like 0 minus what is that, T z by F or something, or F square, I believe, whatever. But you can actually verify all this. I don't know whether it's actually F square or F, but I've written it as F square. I think it is F square, 0 0 0 0 0. Okay, and again you can scale this. This is again only up to a scale. Therefore, you can say that equivalently this is 0 minus 1 0 1 0 0 0 0 0. Okay, that's my fundamental matrix corresponding to the forward translational case. And now I can ask, right, what is this in null of this? And you can show that the null of F, right, again if you do an SVD, right, you can show that this is 0 0 1. By the way, right, I mean if you try to, okay, first let's find out where does a point map, right? So where is the epipolar line? So let's take 0 minus 1 0 1 0 0 0 0 0. I apply it on a point xy1 in my left image, or no, not left image, now it's the first image, right, and this gives me minus y x 0. This is my say epipolar line, and now we want to look at x dash y dash 1 for it to lie on this epipolar line, right. This should be equal to 0, right. We should satisfy this condition if it has to lie on this, which then means that minus x dash y plus x y dash is equal to 0, which then means that your x dash is x and y dash is y, right. Now what does that mean? Right, that means that, see, I mean you need actually 2 points to tell where the epipolar line is, right. One point is this, if x y, so on my right plane, image plane, right, I am saying that if on the left I start at x y, then my x dash and y dash are both again mapping to the same x y. The other thing is the epipole itself. The epipole is this E vector is 0 0 1. That means it's the origin, right. So the epipolar lines look like these.
Because all these lines
Pass through the origin. So all the epipolar will pass, and that's what you actually see. You know, if you walk with a camera, right, you get the zoom in and zoom out effect, right. That's because all the points are either moving towards the epipole or they are sort of moving away. I mean, that's I don't know how many of us pay attention to all this, but really, right, that's what will happen. And the nice thing is, this is even the scene is 3D and everything, right, doesn't really matter. Okay, so yeah, so these two cases are actually, right, good to know, just to have a feel for, right, I mean, you know, what is, where the epipole might be, or how the right, how these right epipolar lines could turn out to be, or where you should search and so on. Okay, now let's again right, get back to this. Okay, yeah, there is one topic, right, which we will not cover. Okay, that is I think I clicked on something. Okay, now what is called actually rectification. what is called rectification. Camera rectification it's called. It's not your rectifier, right, that you learn in electronics. So there is something called camera rectification, right. I will not actually talk about this. The rectification is actually a nice operation. It's actually consists of just homographies, right. You might wonder, if you are interested, read it. Okay. So this rectification operation is such that if you give me non-converging cameras, right, then I can rotate them in a manner that they actually come back to a parallel configuration. That is actually a rectification, and it doesn't involve any translations, it doesn't involve anything, it involves rotational homographies. The moment you say that translation is involved, then it means that, right, the 3D and all it will come into the picture, right. It's scene independent, it's got to do with the cameras alone, and this is fairly involved. Okay, we don't have time to, right, go through this rectification process, but for those of you who are interested, you can read about it. I will not ask, right, anything on this in the exam, but I just wanted you people to know that this is precisely done for this reason, that when you have a parallel camera setup, the search is so easy, right. You just have to go along the same row. Whereas the moment you have any other configuration of converging cameras, then right, every time you have to wonder where the epipolar line and so on. Therefore, right, rectification is actually a standard procedure. You have a camera pair, stereo camera pair, because nobody knows, right, whether they were set up in the correct way. There could be a mutual rotation or something. So right, rectification they will anyway do. It's a standard procedure. But the interesting thing is that it can be done as actually rotational homography. So if you remember homography, if you do rotation, right, 3D should not matter, right. The scene depth doesn't matter for rotations. Okay, and yeah, so it's an entire topic in itself. Okay, so just remember that right, that basically typically when, let's say, people do stereo, right, what they really mean is this. Okay, that is, they have a rectified pair. That's called a rectified stereo pair, because then that makes the search and everything very sort of easy, right. It's a kind of a convenient thing to do. Then the next thing, right, that I wanted to talk about was, yeah, right, estimating f itself. Now all the time, right, we have been assuming that we know f, right. I mean, we wrote down f as some k something and all, right. Now f, so computing the fundamental matrix. See, this whole thing is a lot more involved, by the way. Okay, I am only telling things that are most relevant. Okay, actually, this geometry is not an easy thing. It's very interesting, but at the same time, there are several things, right, that one has to be aware of. I mean, I'll try to talk about something like what is called ambiguities. Like for example, right, you see, it's not true that if you take a camera setup. I should not say this now because you will get more confused. But the point is, right, when somebody, okay, one of the things that you should realize is when somebody shows a depth map, just as you have an image, right, when somebody says I have a depth map, right, what they show is again an image, right, they don't show a 3D scene, right, they show an image. What does that mean? That actually means that, and then if you look at that image, right, it will have like simply grayscale values. It won't have this color and all. Sometimes people can show it in color, but normally it will be a grayscale image, where let's say bright points will typically mean that something is near and dark points will mean that something is far. And the way you have to interpret that is a depth map is that right from the camera center, right, through that image coordinate that you have, if a ray had passed and kind of hit a point somewhere in the 3D scene, then the z component of that particular guy with respect to this camera is that depth, right. That is a way to actually interpret that. No, yeah, right. Okay, now let me ask you a question. So in the parallel camera case, right, I have a depth map, right. Let's say I take the left camera, I see a scene, right. In front of me there is actually a 3D scene, right, and assume that somehow if I can get the correspondence, then I can compute depth. As we know, right, once you know a disparity, that means if this disparity is high, then we know that the point is probably close to the camera. If the disparity is low, then we know that the point is farther to the camera. That we know, right. That comes from that is fx by z. Except that we have to explicitly show that now, which we will do today.